In the early 19th century, the scientific world buzzed with the mysteries of electricity and magnetism. These two forces, though seemingly distinct, captivated the minds of many great thinkers of the time. These forces seemed both magical and separate, each with its own set of rules and phenomena. Benjamin Franklin, with his kite and key, had famously demonstrated the electrical nature of lightning, a groundbreaking experiment that electrified the scientific community. But magnetism, the force that drew iron filings to lodestones, remained a separate enigma, shrouded in mystery and wonder. Hans Christian Ørsted, a Danish physicist, provided the first clue to a deeper connection between these two forces. In 1820, he noticed something peculiar during a lecture demonstration that would change the course of scientific history. As he passed an electric current through a wire, a nearby compass needle twitched, indicating an unseen force at play. This simple observation sent shockwaves through the scientific community, suggesting a hidden link between electricity and magnetism. It suggested a fundamental link between electricity and magnetism. The implications were profound, opening up new avenues of research and experimentation. If electricity could influence magnetism, could the reverse also be true? This question intrigued many scientists. Could magnetism somehow generate electricity? This idea sparked a wave of curiosity and experimentation. These questions spurred a new era of investigation, setting the stage for the remarkable collaborations of Faraday and Maxwell, who would go on to revolutionize our understanding of these forces. Enter Michael Faraday, a self-taught scientist with an uncanny intuition for the unseen forces of nature. Faraday, unlike many of his contemporaries, was not bound by the constraints of complex mathematics. Instead, he possessed a remarkable ability to visualize abstract concepts. Faraday imagined the space around magnets and current-carrying wires as being filled with invisible lines of force. These lines, he proposed, represented the direction and strength of the magnetic and electric forces at play. Where the lines were close together, the force was strong. Where they spread apart, the force weakened. This revolutionary concept challenged the prevailing Newtonian view of action at a distance. Instead of forces acting instantaneously across empty space, Faraday envisioned a medium, an ethereal field through which these forces propagated. His ideas, though radical, laid the groundwork for a profound shift in our understanding of the universe. James Clerk Maxwell, a brilliant Scottish physicist, was captivated by Faraday's elegant but qualitative descriptions of fields. Maxwell, a gifted mathematician, recognized the need to express Faraday's ideas in the rigorous language of mathematics. Through a series of elegant equations, now known as Maxwell's equations, he achieved just that. These equations provided a complete mathematical framework for describing the interplay of electric and magnetic fields. But they did more than that. Hidden within these equations was a stunning prediction. Maxwell's equations showed that changing electric and magnetic fields could propagate through space as waves. Furthermore, these waves traveled at a speed remarkably close to the speed of light, which had been measured with increasing accuracy. This led Maxwell to a breathtaking conclusion. Light itself was an electromagnetic wave. Maxwell's prediction of electromagnetic waves was revolutionary, but it remained unproven for over 2 decades. His equations suggested that light itself was an electromagnetic wave, a concept that was both groundbreaking and controversial at the time. Then, in 1887, a German physicist named Heinrich Hertz devised a brilliant experiment to test Maxwell's theory. Hertz was determined to provide empirical evidence for these theoretical waves. Hertz generated high-voltage sparks across a small gap, creating rapidly oscillating electric and magnetic fields. These fields, according to Maxwell, should propagate through space as waves. If Maxwell was right, these oscillations should propagate through space as electromagnetic waves. This was a critical test for Maxwell's equations and the very nature of light. To detect these invisible waves, Hertz used a simple loop of wire with a small gap. This loop would act as a receiver for the electromagnetic waves. He reasoned that the waves, if they existed, would induce a current in the loop, causing a spark to jump across its gap. This would be the definitive proof of their existence. And indeed, as Hertz generated sparks across his transmitter, he observed faint sparks jumping across the gap in his receiver, even though it was some distance away. This was a monumental discovery. He had successfully transmitted and detected electromagnetic waves, confirming Maxwell's prediction and ushering in a new era of wireless communication. This experiment laid the foundation for modern technologies like radio, television, and even Wi-Fi. Section 5. The race to wireless, Tesla, Marconi, and the broadcasting revolution. Hertz's confirmation of electromagnetic waves ignited a technological firestorm. Inventors and entrepreneurs raced to harness these invisible waves for communication. Among them were two towering figures, Nikola Tesla and Guglielmo Marconi. Tesla, a brilliant and eccentric inventor, envisioned a world powered and interconnected by wireless energy. He developed key technologies such as the Tesla coil for generating and transmitting powerful radio waves. Marconi, an Italian entrepreneur, focused on developing practical wireless telegraphy systems. He established the first successful commercial wireless communication company and, in 1901, famously transmitted the first transatlantic radio signal, proving the feasibility of long-distance wireless communication. The race between Tesla and Marconi, though often marked by rivalry and patent disputes, ultimately led to the birth of radio broadcasting, a technology that would transform how we consume information and entertainment. Section 6. Maxwell's enduring legacy from relativity to modern technology. Maxwell's equations stand as a cornerstone of modern physics, their impact extending far beyond the realm of electromagnetism. They provided the framework for understanding light, paving the way for modern optics and telecommunications. But perhaps their most profound influence is felt in Albert Einstein's theory of special relativity. Einstein, while still a young patent clerk, was troubled by an apparent inconsistency between Maxwell's equations and the laws of motion as formulated by Newton. Maxwell's equations implied that the speed of light was constant for all observers, regardless of their own motion. This contradicted the Newtonian view, in which velocities simply added up. Einstein, in a stroke of genius, realized that it was Newton's laws that needed revision, not Maxwell's. This realization led him to develop his groundbreaking theory of special relativity. Section 7. Einstein's inspiration building on Maxwell's foundation. Einstein's fascination with light, spurred by Maxwell's work, became a driving force in his scientific journey. The constancy of the speed of light, a consequence of Maxwell's equations, was a puzzle that captivated Einstein's imagination. He envisioned a thought experiment. What would it be like to chase after a beam of light? According to Newtonian physics, one could eventually catch up to the light wave. However, Maxwell's equations insisted that the speed of light remained constant, regardless of the observer's motion. This apparent contradiction led Einstein to a profound realization. Time and space were not absolute, as Newton had assumed, but were relative, depending on the observer's frame of reference. This insight, born from his struggle to reconcile Maxwell's equations with the laws of motion, formed the bedrock of his theory of special relativity. Section 8. Light's duality, wave and particle in quantum mechanics. Maxwell's electromagnetic revolution, while profound, was not the final word on the nature of light. In the early 20th century, the emerging field of quantum mechanics revealed a surprising duality. Light could behave as both a wave and a particle. This wave-particle duality, a central concept in quantum mechanics, challenged the classical view of light as solely an electromagnetic wave. Experiments such as the photoelectric effect demonstrated that light could also behave as discrete packets of energy called photons. This surprising duality, though seemingly paradoxical, has been repeatedly confirmed by experiments. It highlights the limitations of our classical intuitions when trying to grasp the bizarre yet elegant world of quantum phenomena. Section 9. Conclusion: an unseen revolution still shaping our world. The unification of electricity, magnetism, and light into the single phenomenon of electromagnetism stands as one of the greatest triumphs of 19th century physics. This groundbreaking discovery not only revolutionized our understanding of the natural world, but also paved the way for countless technological advancements. It was a revolution driven by the combined genius of Faraday and Maxwell, whose legacies continue to shape our world. Their collaborative efforts and individual brilliance laid the foundation for modern physics and engineering. Maxwell's equations remain a cornerstone of modern physics, underpinning our understanding of everything from radio waves to the behavior of stars. These equations are fundamental to the fields of electromagnetism and quantum mechanics. They inspired Einstein's theory of relativity and continue to guide our exploration of the universe, from the smallest subatomic particles to the vast expanse of the cosmos. The influence of their work is evident in every corner of scientific research. The invisible waves that so captivated Faraday and Maxwell have become an indispensable part of modern life. These waves are the backbone of our communication systems and many other technologies we rely on daily. They connect us through wireless networks, illuminate our homes, and entertain us through countless electronic devices. The impact of their discoveries is felt in every aspect of our daily lives. Their story is a testament to the power of human curiosity and the enduring impact of scientific discovery. It reminds us that the quest for knowledge can lead to revolutionary changes that shape the future.